So what we were doing last time, we introduced this problem, this two-dimensional problem in elasticity. We said we want to solve this kind of a two-dimensional domain, rectangular domain, which is fixed at this point, and there is a traction that is acting on the top surface of this domain. So we started to derive the weak form for any two-dimensional problem. This is not just for this problem. This weak form can be applied to any two-dimensional problem in elasticity. So we went through the same steps. We take our governing differential equation, multiply it with u bar, do our integration by parts, and in that we also need to apply the divergence theorem. So that divergence theorem was right here. You will get this term as the integral over the domain, and if you take that term, that integral over the domain will then become this integral over the boundary. So you can see that the term inside the parenthesis is right here, the same term with the parenthesis. But instead of the derivative with respect to xj, we will have it dotted with the normal vector in the j direction. Okay, so this is the divergence theorem that is coming into play here. So then we further subdivided our boundary into two parts. One is the gamma d, which is the displacement boundary condition, and the rest of the boundary, which is gamma n. That's the traction boundary condition. We said that our virtual displacement is going to be 0 on the displacement boundary condition, so the only term that is left is this. And we also introduced the Voigt notation into the weak form. So when we use the Voigt notation, we can express our weak form as strain and stress. Instead of tensors, we are going to use the vectors. So the only difference was that in the strain vector, we will use the engineering definition of the shear strains. Okay. So finally, we have this weak form, and we said that this weak form needs to be evaluated. All these integrals need to be evaluated over the entire domain. So we discretize our domain into lots of different elements, and then we just we need to try to evaluate what all these element stiffness matrices and all these element vectors are going to be. So for the particular case of the three-noded triangle, we took a look at all these approximations. So this is the finite element approximation for a three-noded triangle, which is again the same form, n matrix multiplied with the degrees of freedom. So this is something very standard, and you have to make sure you understand these steps. These will be common to all finite element formulations. And then you have your strain, which is just a derivative of the shape function matrix, but there are some terms to take into account the shear strain. So you can make sure that when you multiply this row out with this column vector, you should get the approximate value of strain in the xx component, which is 1, 1. Okay. Similarly, the second row times this vector and the third row times this vector, they should all give you these three quantities, an approximate value of those three quantities at any point in the triangle. So again, this is some general point in the triangle, and this is just going to be an approximation for that value. So finally, you plug that into your weak form, and you try to evaluate all your integrals over one element, and you will have the same sort of setup that we had before. You can find your element stiffness matrix, element force vector, and maybe I should also place a parenthesis here. So and then finally, when you assemble all your element stiffness matrices, you will get the familiar equation K times D is equal to F. Okay. So this is where we stopped about last time, but we also had another page in in the last time's handout, which was about assembly of these elasticity matrices in 2D, which is very similar to the assembly that we did for our heat conduction problem. So this sheet was from the last time's handout, but this is very similar to the assembly that we did for the heat conduction problem. But in the exception here is that there are going to be 2 degrees of freedom per node, okay? And in general, this is true for any vector problem. So let's say you have a 2-dimensional or a 3-dimensional problem, then at each point you will have 2 degrees of freedom or 3 degrees of freedom. And if it is a thermal problem, you can have more, in addition to displacement, you can have temperature, 4 degrees of freedom. You could have many other quantities that you could be solving at the same time. So the number of degrees of freedom per node, that could be a general number depending upon the type of problem that you have. So in general, let's say you have S number of degrees of freedom per node. In this case, there are 2. So the total degrees of freedom in the problem will be S times n, and in this case, if there are n nodes, you will have 2n degrees of freedom. Total number of degrees of freedom are 2n. And if we adopt the convention that let's go to a node, general node in this mesh, let's say go to node number 4, let's call that node I, okay? And if there are S degrees of freedom per node, then the corresponding degrees of freedom for the node I can be written out in this fashion. Okay, so just take an example for this 2 degrees of freedom per node and node 4. So we can see that the degrees of freedom that are labeled for this node 4 are 7 and 8. Right? This is also something that you might have done for your truss problem. Each node had 2 degrees of freedom, and if there is a node 4, the degrees of freedom corresponding to node 4 are 7 and 8. And if you plug in 4 here for I, 4 minus 1 is 3, times 2, 6, plus 1, 7. And 4 minus 1, 3, plus times 2 is 6, plus 2 is 8. So 7 and 8 are the degrees of freedom for node number 4 in this special 2-dimensional case. So in this way, you can write out your general formula for all the degrees of freedom corresponding to a particular node. And the reason that this is important is you are going to code up the same sort of element degrees of freedom, node LDOFs vector that I was telling you about in your MATLAB codes. So you can directly take this and you can code it up into MATLAB for each of the nodes of the triangle. Then those would be the degrees of freedom for the element. And once you obtain this element stiffness matrix, for elasticity, you will have a matrix that will be 6 cross 6. And obviously the reason is that each triangle has 3 nodes, and each node has 2 degrees of freedom. So there will be a total number of 6 degrees of freedom per triangle, okay? And maybe we can draw those degrees of freedom here. So the local degrees of freedom per triangle are going to be 1 and 2, 3 and 4, 5 and 6. And when you start to assemble them, you have to find the corresponding global degrees of freedom, and the exact same command in MATLAB or the formula that you use for assembly is going to be valid here also. You can replace this with LDOFs, this with LDOFs, and this thing will work in MATLAB just the same way that you did for your truss. Okay. So this is basically just the assembly routine for our stiffness matrices, for our force vectors. But let's try to see how to actually calculate some of these integrals. Okay. So we talked about how to calculate the, we have some formulas for our element stiffness matrix, element force vectors. If you just go back to, let me, right here. So once you introduce your approximation, you get that your element stiffness matrix is this integral that needs to be evaluated over the element domain. Your force vector, your element force vector is going to be this integral plus this integral that needs to be evaluated. So this integral needs to be evaluated over the domain of the element, and this integral needs to be evaluated over the boundary of the element, and only that part of the boundary which has some traction specified. Okay. So let's try to take a look at how to evaluate these integrals. So so from the heat conduction problem, before this elasticity problem that we had this vector f that the same type of expression we came up with, that n transpose f over the domain of the triangle and n transpose h over the boundary of the triangle. So in this case, if you try to consider f element, let's say we have the same old problem of that heat conduction, that the top surface is at some temperature and the bottom surface is at another temperature, and you are pumping in heat through this edge, and that heat, let's say in our case, is a constant heat flux over this edge. So this integral, it has an f term sitting in it. So the problem that we set up, we did not have any f term. We said that there is no heat being generated at any point in the domain. So if there is no heat being generated in the domain, then this f can go to 0. But if there is heat being applied to the entire domain point-wise, then that's something similar to the body force. So that will need to be accounted for. But in this case, we need to find which are those elements which have a boundary that is common to the traction boundary. So for example, this element, this has one edge which has heat flux specified onto it. So that is the traction boundary for that element. Similarly, this element has this edge. This element has the free edge, which is also a traction boundary because there is no heat flux being applied there. Okay. So we need to calculate these integrals, and to calculate these integrals, we are just going to expand this into the matrix form. So this n transpose matrix for the heat conduction was this, just n1, n2, n3 arranged in a column vector, times f, which is a scalar, but it could be a general function of x, y. So if you go in your domain some location x, y, then you could have some function for the heat generation at that point. And similarly, the boundary term, you have n1, n2, n3, that is n transpose the column vector, multiplied with h as a function of x, y. So in this case, h needs to be only a value. It can vary with y, but the value of x is constant here. But in general, if you have a two-dimensional domain of a general shape, then your h can be evaluated at any point x, y along the boundary. Okay, so this is a general integral that you could have. Now, how to evaluate these two integrals is the question. And so before we try to see how to evaluate those integrals, let's also consider the forcing term that we just talked about in elasticity. So in elasticity, we have the similar term n transpose b, but unlike the heat flux, which is a scalar, our body force is going to be a vector, right? So in this example, let's say I have gravity that is acting in the negative y direction. Then what would be this b? This b vector, what would be the b vector if I have gravity acting in the negative y direction? Sorry? Rho g, that's the second component of your b vector, right? So it would be minus rho g in the second component. It would be 0, comma, minus rho g, right? So that's the body force. So what I'm saying here is that this force would be 0. This force would be minus rho g, if you want to take into account the self weight of this thing. So what we would have in this case, the n transpose matrix is not going to be just a column vector. This is going to be a 6 cross 2 N transpose matrix, okay? And we have the two boundary terms. If you multiply, the body force terms, if you multiply this out, what you would get is that the element force vector is going to be 6 cross 1, okay? So we need to calculate this 6 cross 1 vector for each and every element in the mesh, and then we just assemble them, and you would have your global force vector, just like the same way that that you did for the truss. So on the boundary term, we again have the same N transpose matrix, but here we have a traction. This is also a traction vector that is acting on this edge. Now this traction, the way I have shown this traction, this is again acting in the negative y direction. So the way I have shown here, this Tn in the x component would be 0, and this component would be minus the value of this traction, okay? So the same thing happens here, and we somehow need to find a way to integrate all these over the edge of the element. So now, in this case, we need to evaluate these integrals over the domain of the triangle, and in this case, we need to evaluate these integrals over the edge of the triangle. So in this case, only the element 2 has a gamma n, and only element 6 has a gamma n. All the other elements have gamma n 0. There is no gamma n for all the other elements, which means that you, to find out what is the load vector, you just need to calculate the load vector for element 2, element 6, and assemble them into your global force vector. Similarly, for these, if you are going to take into account the body force, the self weight, then each of the elements is going to have this element force vector, right? So we'll take a little bit of an example a little later, but let's try to see how we can evaluate these integrals. So the point that I'm making here is that in general, all these integrals will need to be evaluated numerically. The same way that you did for your one-dimensional problem, where you, if you look at the solution, I just coded up k is equal to Ca or Le plus 1 minus 1 minus 1 plus 1 and so on. But the force term, I told you that I could give you any general body force that that you might need to evaluate over the length of the element. So the same thing happens here. To evaluate those integrals, we use in the one dimension, we use the trapezoidal rule. In this case, we will get to numerical integration later, but there are certain special cases where you can actually evaluate these integrals by hand, just the same way that I did for the stiffness matrix. That was Ca over L, 2 cross 2 matrix. We can find those kinds of explicit expressions for all these force vector and the stiffness matrix. For the special case, when let's say your heat flux vector, the body force term is constant, or your edge traction is constant. So for example, in this case, if we apply, if we just consider the self weight, is that a constant body force? If we apply self weight only, that is minus rho g in the second component, is that a constant body force? It's constant body force. So we can apply this this technique that we are going to talk about, and we can come up with explicit expressions so that we don't have to do any numerical integration, and that will go much faster when you implement it on the computer. Similarly, if you take into account, let's say that this traction is varying over this edge in a sinusoidal manner, okay? So this traction would not be constant in that case, and then you would have to use some sort of numerical integration. But the trick here is that even if you have a non-constant f function, what you can do is you can keep on dividing your mesh into smaller and smaller triangles. That is called refinement, right? If you keep on dividing your mesh into smaller and smaller triangles, in the end, you will be able to approximate your sinusoidal force function as a constant function over small edges of the triangle on the top, okay? And that is a valid way to solve, because what we are saying here is that as you keep on refining your mesh, in the end, your solution should converge to whatever was the exact solution. So so even if your force and all those functions are not constant, you can still apply this technique, and you can, but you have to know that that you would have to use a very fine mesh to be able to get a decent answer. Okay. So let's see how to do some of these integrals. Um, so let's consider this domain term first. We have we want to calculate n alpha times f naught, which is a constant force heat flux scalar, and we want to calculate this over the domain of the integral. So let's say this is our element. It has the coordinates x, y, x1, y1, x2, y2, x3, y3, and we want to calculate this quantity. And this quantity would go into this integral right here. So for example, n1 times f naught, n2 times f naught, n3 times f naught. This would give us a 3 cross 1 vector. This is where this quantity is going to go. So in general, if we have n1 and n2 and 3, we are just going to try to calculate for a general node n alpha. And since f naught is a constant, I can pull it out of the integral, and all we need to find is the area or the volume under the shape function evaluated over the domain of the integral. Okay. So we know that if somebody gives us these coordinates x1, y1, x2, y2, and x3, y3, then we can evaluate the explicit expressions for these shape functions. And we saw even last time that these shape functions are given as a linear expression, where so this is something that we did last time, if you remember. Here, so for example, if you have these 3 coordinates 1, 2, 3, you can construct these equations, solve back for your a1, b1, c1, a2, b2, c2, and so on. So using these things, you can express your n alpha in terms of these constants. So if you go back here, I think I might be missing a 2 delta somewhere. Right. So I'm missing a 2 delta here, divided by 2 delta, divided by 2 delta, and divided by 2 delta here also. Okay. So all you do here is you substitute your n alpha to be this, and now we are going to evaluate all these integrals. So let's take a look at the first term. You have a alpha, that's a constant. You can pull it out of the integral, and what you're left with is this. So what is this quantity? That's the delta, that's the area of the triangle. How about this quantity? We can again do the same thing. B alpha is a constant. We can pull it out of the integral. What we are left with is x times d delta. So if I take the integral of that, what is that? Yeah, that's the first moment. It's not the moment of inertia, but it's the first moment of that triangle about the origin. So in that case, what is that going to be? That is going to be the centroid of the x component of the centroid times delta. Does that make sense? So we use this formula to calculate the centroid, right? X component of centroid times delta is equal to x times d, x times the d area, right? Okay, so maybe what I had earlier was correct here. There doesn't need to be a 2 delta here, but we just need to remove this delta. So this is what it should be. Does that sound correct? So we know that n alpha is equal to 1 upon 2 delta times this. 2 delta stays here. We have a delta here. That cancels off with this one. and this delta cancel off, and similarly you will have this quantity, which is yc times delta. So finally, if you plug all these numbers in, you will get this expression that says that if you want to evaluate the force term for a particular shape function, you can express it like this. And the idea is that we have already done this integral exactly by hand so that we can directly code this up into MATLAB. So for example, if somebody gives you the coordinates of 3 points, x1, y1, and so on, and they give you the material properties and what is the F force, or sorry, the heat flux in this case, what is the F that is acting on the domain of the triangle, then using the coordinates and the F, you can write out an explicit expression for each component of your element force vector. Okay. So now, we'll take a look at an example of that, and let's consider the boundary force, the boundary term first. So we have the same sort of expression here. We want to evaluate n1, n2, n3 times h naught, and we want to evaluate only over the part of the boundary that is on which the heat flux is specified. So we are going to write this out in a different manner. We are going to pull this h naught out of the integral, and since the boundary of the triangle is 3 edges, it is possible that all the 3 edges are being given some sort of a heat flux, but in general only 1 or 2 boundaries of the triangle will be specified with a heat flux. So how to do this integral? So whatever we are left with inside is an integral over, let's say, one edge. So in this case, I'm considering this edge that goes from node 1 to node 2. I'm going to call this edge number 1, and what I want to do is I want to integrate this shape function along the edge of this triangle. So let me ask you this. Let's say the node 3. What is the value of the shape function along this edge for shape function corresponding to node 3? So the shape function corresponding to node 3 is 1 here and 0 here, right? So the value of this n3 is going to be 0 all along if you consider edge 1 to 2. So we already know that the third component of our force vector is going to be 0, which leaves us with n1 and n2. So to evaluate n1 integrated along the edge, what we do is we are going to express this edge in terms of a parameter s. So we are going to say that this s parameter is 0 at node 1 and goes up to the value of 1 at node 2. And you can see by just plugging it into this formula that this formula is valid for a parameter s. If s is 0, this term goes away, and what we get is x1, right? That's right here. Similarly, if s is 0, we get y1. So we get x1, y1 for s is equal to 0. If you plug in s is equal to 1, then this term falls off, and what you are left with is x2 and y2. So in going from here to here, s varies from 0 to 1. So this is just a parameter. You have parameterized one of the edges of the triangle. And now you can calculate your integral. So using the same formula that we had a alpha, b alpha, c alpha, we can substitute this parameterization. So you have x in terms of s, and you can substitute this into this formula and get a new function, which will be a function of s now. It won't be a function of x and y. So if you just plug in this value of x from here and this value of y into this point, you would get this expression for s. And note again that this is a linear function of s, and we know how to integrate linear polynomials exactly. So what we are going to do now is express the integral that we wanted before as h naught integral 0 to 1 of this new function. And if you integrate this new function, you will see that what you get is a alpha right here, and integral 0 to 1 of 1 would be just 1 back, so we don't have anything sitting here. What would we get if we integrate this term? So this is a constant term, right? You can pull this out of the integral. Again, you would have 0 to 1. Integral ds, what would that be? So I guess you guys are not following. Let's do this. Okay, so if I want to calculate this integral right here, I'm going to substitute this entire thing into this part, and what we will have is 0 h0 integral 0 to 1 a alpha ds plus integral, so this is the constant term. Let me just express it like this. So we have plus b alpha x1 plus c alpha y1, and this is the term that is with the s, so we will do it 0 to 1 I don't know why it's okay, there we go. And what we have here is this quantity all right, so finally we have s ds. So all I've done here is expressed this n alpha, taken this expression, plugged it in here, and now we want to evaluate what are these terms going to be. So this is an entire constant term. I can pull it out of the integral, and what we would have here would be this a alpha. And the corresponding term that you would get for, you would also get a b alpha x1, right? So what I can do is I can take this term out of the integral, and I know that this thing is just 1, this thing is also 1, or 1 over 2. So what we will do now is we'll see that this x1 over 2 will combine with this and give you this quantity. And so is there something, is there one line missing here for the edge 1, 2? Because this seems to be for the general edge I to j. Let me and this was the term that I was looking for. Right. So if you plug all this in, you will see that x1 divided by 2 comes here, x2 divided by 2 comes here, and so all we are doing is, can you see some sort of a pattern here? in this term. What does this term mean physically? What we were trying to do here was we trying to integrate this h naught, a constant function, along the edge of this triangle. So we already said that n3 is going to be 0, but how about n1 and n2? This n1 is 1 here, 0, 0 at the other two nodes. N2 is 1 here and 0 at the other two nodes. So what should we be getting out of this? This is just an average location of the point that is midway, right? So the value of n1 and n2 at that midway point is both equal to half. So what that means is that if you have an edge with a constant load, you just split half this way, half that way. That's exactly what we do in structural analysis. That's where the half and half comes from, right? So anyway, if you have a general edge, this was an edge 1 to 2. If you have a general edge I to j, nodes I and j, you can express it in the same way, and you will get the load vector that is corresponding to that edge. So let's take a look at an example. Hopefully this should make things a little more clear. So we are going to consider this example that we did even last time. The coordinates of this triangle are given to us: 2, 1, 5, 3, 3, 4. And we are also given that the force or the heat flux vector is some constant, F naught, and there is a constant H naught heat flux vector on this edge. So using the same using the technique that we talked about last time, we can find out what are all these shape functions, right? So if somebody gives you the coordinates of the triangle, you can find out these shape functions by using the method that we talked about. And we saw that A1, A1, B1, C1, and all these coefficients can be expressed in this way. And you can note that all these coefficients are expressed in terms of the coordinates of that triangle. Okay, so we saw that if you use this technique, you will come up with this sort of an expression for the approximate value of the temperature at any point in the domain. And we said that this part was going to be n1, this part is n2, and this part is n3. So in this case, A1 is 11, B1 is -1, C1 is -2, and so on. So using this fact, now we try to calculate all our force vector integrals. So if you write this out using the same formula that we had before, I think there is some error in this calculation. So we are missing a 2 here, is that right? And there should not be a delta here. So two times 7, 2 times 7, 2 times 7, that's in the denominator, and this delta does not need to be multiplied here. Okay, so I guess what I should do here is ask you to do these calculations again, because there's errors in these calculations. But let's take a look at what we were trying to do here. If you go back to that lecture, we also said that the sum of A1, A2, A3, that is going to be the determinant of that matrix, and that determinant was twice the area of the triangle. So we know that 2 delta is going to be A1 plus A2 plus A3, which in this case turns out to be 7, and that's the denominator right here. So delta, the area of the triangle, is 3.5, and now the centroid location. that centroid location is also simply x1 plus x2 plus x3 divided by 3. So let's take a look at that. We have x1 2 plus 5 7 plus 3 10. 10 divided by 3, that's the centroid location in the x coordinate. Similarly, we have 1 plus 3 4 plus 4 8 divided by 3, that's the centroid location in the y direction. So that's the centroid location. And if you use this formula, let me, you will get some number here, here, and here. And what should you get? Anyone take a guess? So all we are doing here is we are integrating the value of the shape function from over the area of the triangle. Right? So for each of the shape functions, the area, this would be the volume under these shape functions. So let me show you the shape functions first. Right, so these are the shape functions, one at node 1, one at node 2, and one at node 3. If we try to integrate n over the domain of the triangle, what should we get? That would be the volume of this volume under the shape function of this node. So that should be 1/3. This should be 1/3. This should be 1/3. You sum them up, you get the total volume under a constant area times 1, right? So what we have in this case, and maybe you should verify that. Does anybody have a calculator here? Times 3.5 is the area of the so what we should get here, if we sum up all these components, we should get f0 times the area of the triangle. So this is if we sum up all these, we should get f0 times 3.5, which is the area of the triangle. Okay. So in the meantime, those of you who are calculating, let's write out. Let's do the second part. This was the first part, which was for the body force term. The second part was for the force on the boundary of the element. So in this case, we have just h0, which is being applied to the edge 1 2. So if you consider this edge 1 2, that's the heat flux vector that is applied on that. Again, pull out h common. What you are now trying to integrate is in 0 to 1 through over the length of that edge. So once again, we will substitute x. That was the expression for x over the edge 1 2. This is the expression for y over the edge 1 2. You integrate. Now this expression is only a function of s. So you can integrate that, and you will see that we come up with a similar form that we had before. And in this case, A1, I think there is a 1 divided by 7 missing somewhere. So these are all 1 divided by 7. Sorry, I think I have made a few mistakes here, but I'll post the corrected version online. And the third component is going to be 0, because the n3 shape function on the third edge is 0. So finally, if you assemble all of them, again, these values are not correct. So what you should get is delta divided by 3 here, delta divided by 3 here, no minus sign, delta divided by 3 here, length of the edge 1, 2 divided by 2, length of the edge 1, 2 divided by 2 here, and there is plus a 0. So that's what we should get. So let me remove this. And this is basically how you would get the element force vector, and now you can go back and assemble this into your global force vector. So very quickly, it won't take that much time, but we can write out the similar expression for the stiffness matrix. This is something that we did last time. So if you remember, k element was equal to integral over the domain B transpose d b omega, and if you remember, B matrix was n alpha comma 1 0 0 n alpha comma 2 n alpha comma 2 n alpha comma 1. So I'm writing it out as a general B matrix. So this part needs to be repeated for each of the 3 nodes. Alpha is the node. So if you plug in alpha is equal to 1, you will get the first component of the B matrix. Similarly, alpha is equal to 2 and alpha is equal to 3. For the 3 nodes, you need to replicate this part. And once again, we are going to use the same expression that n alpha of xy is a alpha plus b alpha x plus c alpha y. Therefore, n alpha comma 1, which is the derivative with respect to x, that just becomes b alpha. N alpha comma 2, derivative with respect to y, that just becomes c alpha. So the stiffness matrix, the element stiffness matrix, would be nothing but integral over the domain times b alpha, c alpha, and this would be, so this, and this needs to be the transpose of that. Okay. And this would be C alpha, B alpha, 0, 0. And this would continue for all the 3 nodes. And similarly, so let me write this as like this. This is node 1, node 2, and node 3. And similarly, we would have this matrix, the D matrix, and we would have the B alpha 0, 0, C alpha, and you would have C alpha, B alpha. This is matrix would continue like that. So we can find explicit expressions for the stiffness matrix. This would be delta, and if you multiply this entire matrix out, that you can just straight away code up in MATLAB. You don't have to do any numerical integration. You would have the element stiffness term. All right, so let's call it a day here. I'll make those corrections and post them online, and we'll do some examples today in the review session at 5:30. All right, so see you then.